Good evening, and thank you for joining us for this live stream astronomy presentation, Medieval Islamic Astronomy with Galen Gisler. I am Ayçin Aykut with Pajarito Environmental Education Center. I will be the moderator for today's talk. PEEC has lots of ways you can interact and connect with nature when we are closed. Please check our website, peeknature.org, for all our online content, including live talks and outdoor nature challenges. We are able to offer programming at this time because of the generosity of our members, donors, and participants. So thank you for your continuing support. Galen Gisler was born in Clovis, New Mexico, and graduated from high school there. With a PhD in astrophysics from the University of Cambridge, he eventually came to Los Alamos, where he worked at the lab for 25 years. Then he and his wife Susan moved to Norway, where he learned not quite enough geology at the University of Oslo, finally returning back to their cozy mountain town, where he enjoys sharing astronomy with all of us.
Hi everyone, thank you for joining us for this live stream talk on medieval Islamic astronomy. For the most part, I will leave my video off so you're not distracted by me, because the more important information will be on the screen in front of you. But I'll turn my video back on when it's time to take questions. So, yeah, the talk is Medieval Islamic Astronomy, and here's a background of a Persian astrolabe from the 18th century, but we won't dwell on that until later on. The real question here is, how do we get from Ptolemy, the geocentric model of planetary motion that was current among the Greeks, all the way to Kepler and modern astronomy? In schools in this country and perhaps in most of Western Europe, we're not taught very much about what went on in these 1200 years in science and astronomy in particular, between Ptolemy and Kepler. But in fact, quite a lot went on in those years. And the main subject was to try to understand the motion of the planets. And you know, if you're living in a world that thinks that the Earth is stationary, and you watch the planets move around the Earth, you come up with a diagram like this. This is actually a photograph that I took in the planetarium, where I centered our point of view on a stationary Earth and watched the planets' motion over a period of many years. So you see, here is Mercury, here's Venus, here is Mars, here's Jupiter. This bright ring here is the sun. So you see, it's a very complicated problem to try to understand all of these motions, these cycles, the retrograde motion of the planets and so forth. And so Ptolemy wrestled with it, as did many others before him and after him, to try to reconcile the motion of the planets with the notion that the Earth was stationary and in the center. Of course, not all the ancients accepted that the Earth was stationary and centered. Aristarchus of Samos, in particular, developed a heliocentric model, one that had the planets going around the sun, and Ptolemy knew of that model, and in fact he remarked that many aspects of the planetary model would be a lot simpler in a heliocentric model, yet he didn't make that leap. So here is a list of names that I would hope that some of them are familiar to you, but my guess is that maybe you've heard of Aryabhata, maybe you've heard of Al-Haytham, or as he's known in the West as Al-Hazen, maybe you've heard of some of these others, but for the most part, you know this name, but you know it in a different spelling. Algorithm, Al-Khwarizmi, algorithm, you know that name. So all of, you know, the fact that you may not be familiar with all these names is not your fault. but I would say it is the fault of the education that you got. And I think it's a shame that we are not taught about the contributions of all of these people. From Aryabhata, we inherited a place value system, which we use every day in our mathematics. We inherit trigonometry, sines and cosines, tangents, cotangents, all that sort of thing. From Al-Khwarizmi, we get the solutions to quadratic and cubic equations. From Al-Battani, we get a much more accurate solar year than Ptolemy gave us, and also a better value for precession. As-Sufi gave us an improved star catalog. Al-Haytham or Al-Hazen was the father of optics, and he's well acknowledged to be that in the West even. And he insisted on physics behind the mechanisms of the orbits of the planets and hypothesis testing. Al-Biruni is one of the most intriguing figures of this whole millennium of workers, and very little is known about him, but we do know that he considered heliocentrism for the model of the solar system, and also elliptical orbits. Al-Bitruji echoed the sentiment of Al-Haytham for physical causes for the elements of the orbits, and At-Tusi developed a device which actually replaced the equant that Ptolemy used. And this device, called the Tusi couple, was used by subsequent astronomers, including Copernicus. Ibn Shatir completed the work of At-Tusi with a drastic reform of Ptolemy, and his model was also used by Copernicus. And finally, Ulugh Beg, whom you might have heard of, built a wonderful observatory in the Central Asian city of Samarkand, and conducted observations of such precision that they were unequaled until Tycho Brahe 2 centuries later. In general, astronomy developed in lots of different parts of the world, including places that aren't shown here. This diagram is simply to point out that contributions were made by lots of people, from the Chinese to the Greeks, over the millennium before the Common Era, and there are elements of all of these things that eventually ended up in the Islamic astronomy that we're going to be talking about this evening, and from then went into the development of modern astronomy. The point is that contact with neighboring cultures, none of these lived in isolation, but contact between and among these various cultures enhanced the values of the science that were being done in each of these areas, and contributed to the modern whole where science is indeed a global enterprise. So what do we mean by Islamic astronomy? I show this map, and I'm going to show it again near the end of the talk to illustrate where these developments took place. The conquests of Alexander the Great of Macedon extended the knowledge of the Greek language all the way into India. And that knowledge of the Greek language persisted for many centuries in this part of the world. The Abbasid Caliphate, which was the largest empire of its time, lasted from 750 to 1258. They were responsible for the translation of over 1,000 texts from Greek, of medicine, of nature, of science, mathematics, and astronomy, and they made it a project of the empire to translate and catalog all these works. If they had not done so, those works might have been lost forever. This work was mainly done in the heart of the Abbasid Caliphate, which was right about here in present-day Iraq, Iran, Syria. The dark circles on this map show the number of scholarly books that presently exist in the Harvard College Library by people who were living in these different places in the Abbasid Caliphate. The white circles within the dark circles are the proportion of scientific books that were published in each of those areas. Of the scholars who produced these works, during the Golden Age, which is really right around the center of this, around 900 to 1100, they were mostly Muslim, but not all. Some were Christian, some were Zoroastrian, some were Jewish, some were indeed Buddhist. Most of them wrote in Arabic, but some wrote in Persian. They were also ethnically diverse. So it's kind of a misnomer to speak of Islamic astronomy, but we use it as a shorthand, because to say Arabic astronomy is also a misnomer. To say astronomy of the Middle East, likewise, because it extended all the way to Spain. So we call it Islamic astronomy because it was the astronomy that was produced when Islam was the dominant religion of the greatest empire of its time, the Abbasid Caliphate. We begin with star tables, and if star tables, we begin, of course, with Ptolemy, because we don't have any tables that were earlier than Ptolemy, although earlier star tables were certainly available to him. And what I want to point out in looking at these star tables is how we get the names of the stars that we presently know in the sky. And I would be showing this in the planetarium, but of course we're closed, so I can't quite do that, but I'll show you some, the original Greek and a translation by Claudius and Toomer, which describes all of these stars in terms of their position in kind of an anatomical sense with respect to the small bear, the Ursa Minor. So there's a star on the end of the tail, the star next to it on the tail, the star next to that, and the one that joins the body, and so forth. And so none of these actually have names. So I've named two of these that we know today. Polaris, of course, is our present-day pole star, but it wasn't the pole star for the Greeks, nor was it for the Arabs of the 10th and 11th centuries. Polaris has only become our pole star in the last 200 years or so. Let's go on to an examination of the constellation Leo, where we can talk about how these names actually came to us from the Arabic. So we have a few stars here. There's a star Regulus, which appears to be, and indeed is, a Latin name, not a Greek name. And then these names, Adafera and Algieba and Denebola, which are in principle Arabic names. They refer to the anatomy of the lion. So here's a diagram of the lion, for which Leo is the constellation. And you have to acknowledge that the Greeks and the Arabs all the way through knew the anatomy of these constellations by heart. And so they could refer to the star, for example, as Ras al-Asad, as the head, Ras, of the lion, Asad. And they refer to the star next to it, to the south of it, as Al-Janubi, which means the southern one of the head of the lion. So we look at the translation by Claudius and Toomer of the constellation Leo, and we have, I'll put up the modern names of it. The northernmost of the two stars in the head, that's what Ptolemy wrote and translated by these guys, Ras al-Asad, the head of the lion. The southernmost of these, Al-Janubi, the southern one. We can also we could go through all of these, but I won't. Denebola is Deneb al-Asad, the tail of the lion. And so those of you who know Cygnus will recognize as well Deneb as the tail of the swan. So the bulk of the names of the stars that we have in the sky come to us from Arabic, starting out by this anatomical description that was provided by Ptolemy, translated literally into Arabic, and then we just simply take a shorthand of the longer Arabic description as the modern name of the stars. So that's how we got most of the star names. Not all, but a good many of them. In fact, the star Regulus, which we call Regulus, that's a Latin name, as I pointed out. Ptolemy calls it Basiliskos, which is equivalent to the Latin Regulus, meaning little king. So he didn't even call it Regulus, he called it Basiliskos. The story of Islamic astronomy is summed up in this word, Zij, which is beautiful, written in Arabic or Persian. It's a Persian word actually, but you see it most commonly in Arabic manuscripts. Zij. Plural in Arabic is azyaj. The Arabs like to break their words apart when they make plurals. But these were handy books, the zijes or azyaj, that held lots of information about how to do astronomy and much more besides. And in fact, a typical Zij has everything from calendrical conversions to geographical tables, a star catalog, and indeed astrological tables. It had planetary theory, it had the equation of time, it had trigonometry, it had all of these things in it. So these were substantial books, sort of hundreds of pages long, and were maintained in libraries. There are presently some 200 azyaj that are known today, that are preserved, but many more of them were written and have since disappeared. Unfortunately, very few of these documents have been translated into Western languages, and none of them, as far as I can tell, and I've looked very hard, can be accessed in complete facsimile form via the internet. If any of the audience knows of a possibility of getting hands on a facsimile Zij, I would be very glad to hear of it. Otherwise, you would have to visit the Bodleian Library at Oxford or such places to access them with, of course, your gloved hands. If these were more widely available, they would be extremely valuable resources for the history of astronomy and other sciences. So the first Zij that we are aware of was written by this man whose name is familiar, Al-Khwarizmi, a Persian who worked in Baghdad, who formulated, as I mentioned, the solution of quadratic and cubic equations. Those formulas that you learned in high school of how to solve a quadratic equation, this man is responsible for the first form of them. He also introduced to the Arabs the Hindu place notation and decimal system, which we call our numbers Arabic numerals, but in fact they came from the Hindus via this man Al-Khwarizmi, and then eventually to us in the Middle Ages. This book is the first page of his Kitab al-Jubiri, which is the plural of al-Jabr, which means algebra. Al-Jabr, completion, actually is what it means. We take the word algebra from that. So he gives us this word and the word algorithm from his name. He wrote the first of the Arabic Zijes. He, in fact, he used extensive tables from trigonometry that he got from the Hindus. He had his own model for the solar system, which was non-Ptolemaic. It was still geocentric, but it was not quite as accurate as Ptolemy's, and so it was soon replaced by the Arabs afterwards. Muhammad ibn Jabr ibn Sinan al-Battani, who's known in the West as al-Battanius, an Arab who worked in Raqqa, present-day Syria, he made the first very accurate determination of the solar year. Ptolemy, had measured the precession of the equinoxes, but he estimated the precession to occur at a rate of about 1 degree per century, and al-Battani measured it to be 1 degree per 66 years. The modern value that we use today is 1 degree and 71.6 years. So his value of 1 per 66 is much closer to the modern value than Ptolemy's 1 in 100 years. In addition to that, he also corrected Ptolemy with better tables of the motions of the sun and the moon, and these were authoritative basically up until Copernicus. He was the first to discover the apsidal precession of Earth's orbit, which had not been noticed by Ptolemy or earlier astronomers, and that was later improved by the Toledan astronomer Al-Zaghali. And both of these, Al-Zaghali and Al-Battani, were quoted by Copernicus. Yeah, we can answer questions later. The question came up about, yeah. Then there was As-Sufi, who was known in the West as Az-Zofi, another Persian who worked in Shiraz. He was the first person to describe the Andromeda Nebula, which is kind of surprising because the Andromeda Nebula, after all, is visible to the naked eye, and Ptolemy must have noticed it. But I've looked extensively through Ptolemy's Almagest and do not find a mention of a cloud of stars or a cloud of fuzzy stuff in the vicinity of the Andromeda constellation. He also identified the Large Magellanic Cloud. We call it the Magellanic Cloud. We perhaps should call it the As-Sofi clouds. The Large Magellanic Cloud, it was visible from Yemen, but it was not visible from Alexandria, where Ptolemy worked. And he made important corrections to Ptolemy's Almagest. So here's one page from his siege, which illustrates the constellation Gemini. And on the left are his descriptions in words of the various stars of the constellation. And these, many of them, not Castor and Pollux, which are, again, words from Greek legend, but the others have been given to us from the Arabic. And his star catalog was widely used in the West and was only improved upon by that of Ulugh Beg nearly 5 centuries later. So here's Ursa Minor again, Ptolemy's account of it, and As-Sufi's account of it in his siege. And then Ihsan Hafez has translated Al-Sufi's from Arabic into English, and we see that it's basically very much the same as, the anatomical descriptions are very much the same as Ptolemy's, but then he also introduces some Arabic names in there, which did not survive to our present day IAU system. Al-Haytham, Hassan ibn al-Haytham, worked in Cairo. He was an Arab. He published a book called Doubts Concerning Ptolemy. He wrote, Ptolemy assumed an arrangement that cannot exist, and the fact that this arrangement produces in his imagination the motions that belong to the planets does not free him from the error he committed in his assumed arrangement. For the existing motion of the planets cannot be the result of an arrangement that is impossible to exist. For a man to imagine a circle in the heavens and to imagine the planet moving in it does not bring about the planet's motion. Blistering critique of Ptolemy. I love it. So basically he's saying that in order to have a model of the solar system, we must have physics behind it. We must have something that keeps it in order, that keeps the things moving. You can't just imagine these circles, these epicycles, these equants, these deferents, and say that they must exist simply because it, as they say, saves the phenomena. That is, that it interprets the phenomena that we see. We have to we can't just interpret and predict. We have to explain. And Al-Haytham was kind of a pioneer in that kind of physical reasoning. In addition, he's known as the theory of optics. He's widely referred to among all early opticians in the West. His laws of refraction and reflection were later developed and improved upon by Snell. And he did lots of experiments with lenses and mirrors. Here's a photograph of an Iraqi 10,000 dinar banknote. And if you blow up this little segment of that banknote, you can see one of his diagrams, which comes from his book on optics. Evidence that he was well known in the West comes from this book by Johannes Hevelius, who was a Polish astronomer in the 17th century. He built an observatory and wrote this book called Selenographia, which this book includes a description, a detailed description of the surface of the moon. In addition, Hevelius discovered several comets and recorded sunspots. And on this frontispiece, he celebrates both Al-Haytham, who is shown here with one of the diagrams from his optics book, and Galileo, who is shown here with his telescope. And down here at the bottom of this imagined monument are the words Alhazen and ratione, meaning theory, Galileos, and sensu, meaning observation. So these two predecessors of Hevelius were touted here on the cover of this book as the embodiments of theory and observation, kind of a forerunner of the modern way in which we divide science between theory and observation. Abu Rayhan al-Biruni is in many respects one of the most enigmatic and interesting figures of this whole epoch. He speculated on the possibility of the rotation of the Earth. He said, "The rotation of the Earth does in no way impair the value of astronomy, as all appearances of an astronomic character can quite as well be explained according to this theory as to the other. For in both cases, it does not affect the astronomical science. It is just for the physicist to see if it is possible to resolve it." He obtained eclipse data, which we have used in the centuries since to measure the change in the moon's distance from the Earth. Most of what we know of him is actually from an extensive correspondence that he carried on with Ibn Sina, whom the West knows as Avicenna. And in this correspondence, because his manuscripts don't seem to exist, but we do have the letters that Avicenna, that were preserved in the library for Avicenna. And al-Biruni criticized Aristotle on many points, but in particular, Aristotle's view that vacuum cannot exist. Al-Biruni showed by very simple experiments that it can, experiments that in fact you can carry out in your kitchen sink. Aristotle also regarded elliptical orbits impossible because they would create vacuum, which cannot exist, of course. In his writing to Avicenna, he wrote that he was amazed by the weakness of Aristotle's argument against elliptical orbits. Another contribution that we owe to al-Biruni is the division of the hour into 60 minutes and the division of the minute into 60 seconds, using the sexagesimal system that was handed down from the Babylonians to the Greeks and to the Arabs. He also divided the second into thirds and fourths, also by units of 60. But we don't use those. We instead use milliseconds and microseconds, nanoseconds, and so forth. We like a decimal system better than a sexagesimal one. So despite these views that were beyond orthodox, he nevertheless held to the, at least publicly, held to the conventional geocentric view with stationary Earth and circular orbits. Al-Vitruji was another one who tinkered with planetary theory, and he proposed an alternative that avoided epicycles and eccentrics, but nevertheless, it was not a heliocentric system. It was not very successful, but it was introduced to Europe and was debated well into the 16th century. His book, Kitab al-Hayya, was translated into Latin as De Motibus Celorum, which means on the motions of the heavens. This book was popular in Europe from the 13th through the 16th centuries and was used and cited frequently by Copernicus. Again, with al-Biruni and al-Haytham, he demanded that celestial motions must have a physical cause. Then we move to Nasir ad-Din at-Tusi. Lived in the 13th century Persian, worked in Nishapur. He built an observatory at Maraga, made precision observations with it. He speculated in his writing that the Milky Way might be composed of many very distant stars. He couldn't prove that with his observations. He's shown using a telescope, but it's doubtful that he had any such device. On this stamp from Azerbaijan, it was probably just a tube that he was looking through. I don't know, perhaps, I mean, al-Haytham preceded him, perhaps there were telescopes around there, but if they existed, we don't know about them. He invented a device called the Tusi couple, which basically did away with Ptolemy's equant, but still lacked a physical cause. And this device was used by Copernicus, who assuredly knew of at-Tusi's work. In addition, he anticipated Copernicus's use of comets as an argument for Earth's rotation. How does that work, you might ask? If the Earth rotates, then the lower atmosphere must rotate with it, else we would be feeling very strong winds. But comets were thought at the time to be upper atmospheric phenomena. And they follow more or less, not exactly, but more or less, the day-to-day motion of the fixed stars. So the lower atmosphere could be following the Earth's rotation, while the upper atmosphere could be independent of it. Comets were problematical for many of the early astronomers, largely because they're north-south motions, motions that were perpendicular to the plane that all of the planets moved in, were problematic for a Ptolemaic system, or indeed for any geocentric system. Here's a page from one of his books which describes the Tusi couple. Ibn Shatir followed on from Tusi and followed on from another fellow by the name of Mu'ayyad ad-Din al-Urdi, who had a similar device. The Tusi couple and the Urdi lemma, as it's called, both of them were used to replace the equant and deferent. He had a very sophisticated model for basically all the planets. And it turns out that his system was mathematically equivalent to that developed by Copernicus. The only difference was that Ibn Shatir's model, like all of the other models that we know of from the Islamic world, were geocentric and not heliocentric. But I'll try to show that that's in fact a trivial difference. Here's the Ptolemaic model for a typical planet. You have a circle with a center, and the Earth not at that center, but at a point called the eccentric. Then you have another point called the equant, and the orbit of a planet goes around the equant, and then there's an epicycle that goes around the equant point on that circle, and that describes the motion of a typical planet. Most of the planets were somewhat more complicated than this, but this is basically the essentials of the Ptolemaic system. So problems with the Ptolemaic system induced people like At-Tusi and Al-Urdi and Ibn Shatir to introduce other elements to it. And so this diagram becomes rather more complicated to understand. Here's the Earth, here's Ptolemy's orbital center. There's the epicycle circle that Ptolemy used. Tusi used a different point. Urdi used yet another point. Ibn Shatir combined the two of them to produce a model that was somewhat more accurate than all of them combined. Rather complicated. So the assertion I made just a minute ago that his model was basically equivalent in a mathematical sense to that of Copernicus is illustrated by this diagram. This is the Ibn Shatir model for Venus, which includes all of the elements of Venus, with the Earth at this point O, the Sun at F, and Venus at P, and these other points are the positions of the equant, the Urdi lemma, and the Tusi couple. You take this model and you shift it so that the Sun is at F. The sun was at F here, but you move the Sun to the center of this entire diagram, and the Earth over here at O, and you have a model which is geometrically and mathematically equivalent to that of Ibn Shatir, and this is the model that Copernicus used for Venus in his book, De Revolutionibus. The difference here is only the difference in reference frame. And of course, I remarked before that the Copernican heliocentric model is not really new when he introduced it in 1543, because Aristarchus in the 3rd century BCE and Al-Biruni in the 11th century, among many others, had considered heliocentric models. Here's the sketch that was widely circulated for Copernicus model, which doesn't include all of the details that were necessary to make the observations fit the model, which were incorporated in that diagram that I showed just now. But from this, so here, Mercury, Venus, the Earth, Mars, Jupiter, Saturn, and the sphere of the fixed stars, the immobile sphere of the fixed stars. From this, it's clear, and from his writings as well, that Copernicus was very much a medieval astronomer. He still had purely circular orbits and had to rely on epicycles, equants, and the 2C couple to match the observations. His thinking was medieval and highly reliant on his predecessors in the Arabic-speaking world. And in fact, much of the early criticism of Copernicus, just like Al-Haytham's criticism of Ptolemy, centered on the fact that he had no physical motivation for the various mechanisms that enabled his model to fit the observations. The physics that Copernicus lacked was in 1543, when he published, was provided later by Kepler in 1609 with elliptical orbits, and Newton in 1687 with the theory of gravity. Kepler tried a whole bunch of different things, including fitting orbits inside of regular polyhedra and so forth, ovoid orbits and so on, until he finally settled on elliptical orbits. And he remarked that he was surprised that since elliptical orbits are really so simple, that no one had considered them before. But in fact, we know that people had, in particular Al-Biruni, had considered elliptical orbits. Among the last of the great Islamic astronomers was Ulugh Beg, a Turco-Mongol. Of course, this is after the Mongol invasions of the Islamic Empire, which really destroyed the Abbasid Caliphate. But Ulugh Beg built an observatory in Samarkand in Central Asia, present-day Uzbekistan, I believe. This observatory anticipated Tycho Brahe's Uraniborg, which was built about a century later, and they are so similar, in fact, that we're almost certain that Tycho Brahe knew of this observatory and based his upon it. He made precision measurements of planets and over 1,000 stars with his mural quadrant. I'll show you a picture of that, and produced the best star catalog between Ptolemy and Brahe, which was rivaled only by that of Sufi. In addition, as a mathematician, he published tables of sines and tangents accurate to 8 decimal places. Here's a better picture of the observatory of Ulugh Beg in Samarkand. I would love to visit this someday. Perhaps some of you in the audience have visited it. If you have, I would love to have your impressions and photographs of it. This picture is just taken from Wikipedia. And here's another Wikipedia picture taken of the inside of that mural quadrant. There, up at the top, where you can't see above this picture, is where light is allowed to come through from stars, and the observer sits on these various steps and makes measurements of where that star is with respect to a wire that is strung across that opening. Here's Ulugh Beg's star catalog, which is translated into French by Edward Knoebel. And we notice in comparing with Al-Sufi, and likewise back to Ptolemy, the very great increase in precision of his catalog. Finally, and this one is one that Ayçin pointed out to me, a Turkish astronomer by the name of Taqi-ad-Din ibn Maruf, who built an observatory in Istanbul, the Istanbul Observatory. It was contemporaneous with Tycho Brahe's Uraniborg, and I'm convinced that as with Ulugh Beg, Tycho Brahe knew of this, and Ibn Maruf knew of Tycho Brahe, and they compared notes in the construction of their observatory. This was built in 1569 by imperial edict, destroyed by the state only 11 years later. At least the one in Samarkand persists. Before we began, Ayçin told me a little story about the destruction of this observatory, and maybe she can elaborate on that once I'm done. So the question, what went wrong? The Islamic cultures clearly led the world in science, astronomy, medicine, physics, chemistry, and mathematics from 800 to 1400 of the Common Era. Thinkers like al-Biruni, at-Tusi, Ibn ash-Shatir made crucial mathematical improvements and speculations that anticipated the modern heliocentric model of the solar system. And even though they were buttressed by physical arguments by folks like Al-Haytham, they never made the break with the orthodoxy of a geocentric model, stationary Earth and circular orbits. Why not? And why didn't Islamic science prosper after 1400? Now, we have to be careful here because there are today many modern Muslim scholars and scientists, including some at the very highest caliber, some who have won the Nobel Prize in Muslim countries. But they function, for the most part, in the scientific culture that has prospered in the modern world as a whole, including Europe, the Americas, China, Japan, and India. This question, what went wrong, specifically refers to the non-participation in the scientific revolution that occurred with the Italian Renaissance, for which Islamic scholars had indeed laid the foundations. It's not a trivial question. And indeed, this question has received a lot of attention from scholars and historians, both in the Western world and in the Islamic world. These 3 articles are just a few of the many that turn up in an internet search. Some of the answers that these people and others come up with are, well, the Islamic Caliphate was destroyed by the Mongol invasions in 1258. The downfall of that large, wealthy empire led to political upheavals which made it harder for scholars to work. Was there also a decline of rationalism and secularism that occurred at around that time, a conservative religious revival, and a rise of fundamentalism? All of these articles here focus on different aspects of these different hypotheses and come up with somewhat different conclusions. But basically that to some degree, all of these things were involved. I want to show this map again to make a point. So the Abbasid Caliphate, which, as I say, ended in 1258 with the Mongol invasion, was a huge empire. And the political power of that empire and the safety and security of belonging to a great state enabled arts, literature, and sciences to flourish. This empire was highly urbanized and had sophisticated networks of trade and travel and communication, and had Arabic as a single common language, Persian as a secondary language, kind of like the Roman Empire had Greek and Latin as common languages. Some of the scholars who produced these works were religious skeptics, but others were not. Others were strong in their faiths, whether they were Muslim, Christian, or Zoroastrian, or Jewish. This paper down here by Cheney showed that a decline in the production of scientific books began in about 1100, so considerably before the end of the Abbasid Empire. And it started in the center and spread gradually to the east and to the west. In his paper, he shows a diagram here, which on the left scale has the proportion of scientific books among all of the books in the Harvard College Library produced by Arab scholars from the Abbasid Empire during these years as a 50-year running average. There's a sharp decline right around 1100. On the right scale is the proportion of books that were published on madrasas, the religious schools that excluded education in science that had a sharp rise at about the same time. So you have the scientific production going along at a fairly steady rate and then abruptly declining. Of course, there were, people like Al-Biruni and so forth, and eventually Ulugh Beg way out here, still were able to contribute to science, but their works were much less than the works that were produced by scholars, particularly on religion. Cheney makes the point that this was the crucial development, that it was a rise in an anti-rationalist school of Islam, which is known as the Ash'ari movement, which is actually still prominent today in a number of Muslim countries. Abu Hamid al-Ghazali is the most prominent of the Ash'ari school, and he lived right around that crucial time. He wrote a book called The Incoherence of the Philosophers. In that book, he wrote, "Reason is the enemy because it teaches us to question, discover, and innovate. Science is incompatible with religion because nature is entirely subject to the will of God." In other words, there is no need to study physical laws. There's no need to find out what the laws of nature are because God does what he will with nature. The rise of the school that's associated with al-Ghazali coincides with a decline in skepticism and a decline in rationalistic or scientific scholarly works. It's still prominent in many places in the Islamic world, particularly among Islamists. So the question that I pose now is scientific decline inevitable? We've seen that science in classical antiquity lasted for a period of about 800 years, from 500 before the Common Era to 300 of the Common Era, with the Greeks and mostly and Romans in a subsidiary role. There's a lapse of some time after that before. Well, there was Aryabhata in India, but then Islamic culture started doing science in a serious way in about 800 of the Common Era, and going strong until 1100, persisting at some level through 1400 or so. And then it's not heard from since, until Western culture took over. And Western culture had its beginnings in roughly 1600 CE. Actually, Copernicus was 1543, Kepler was 1609, and it continues more or less to the present day. The decline of science in classical antiquity is documented in Charles Freeman's book, The Closing of the Western Mind, subtitled, you probably can't see that, The Rise of Faith and the Decline and the Fall of Reason. The decline of science in Islamic culture is documented, besides those 3 articles and many others that I remarked upon, by this book by Robert Riley, The Closing of the Muslim Mind. I think he deliberately echoed the title of Freeman's book. And these are both, all of these are reminiscent of Arnold Toynbee's hypothesis that he carries through his massive 10-volume work, A Study of History, or this 1-volume abridgment of it, where he talks about the rise and subsequent, the beginnings, the rise to climax and subsequent fall of different civilizations, and that's a story that is echoed very much by the fairly recent 2011 book by Jared Diamond called Collapse. So perhaps we end on a kind of pessimistic note, looking at how science, had its glory days in classical antiquity, its glory days in Islamic culture, its glory days in science, in Western culture, we hope are not over yet, but these 2 declined, and perhaps ours will too. It worries me to see the rise of religious fundamentalism in our world, in all countries, basically, and growing anti-science denialism. And so I wonder if that foreshadows a similar decline in today's science. With that depressing thought, I will leave you with this beautiful Persian astrolabe constructed in the 18th century, a still living testament to the glory days of Islamic astronomy. Thanks. I'll be around for questions if anyone has.
Thank you, Galen, so much. That was a great talk. I learned a lot. So if you have any questions, please write them into chat window and I will relay the questions to Galen. In the meantime, I have a comment from Nels Hoffman. He says, Al-Ghazali also rejected Aristotelian causality. The great contribution of Thomas Aquinas was to reconcile Aristotle with Christianity.
Yes, that's correct. Absolutely. Yeah, Al-Ghazali was a critic not only of Muslim scholars but also of Greek scholars, and I agree that that Aquinas did Western science a great service by reconnecting us to causality. No, that's a very good point, Nels, and I'm glad you brought that up.
There is a question from Felicia. Is the anti-science denialism associated with Shia or Sunni school of thought? So is anti-science denialism associated more with Sunnis or with Shias? Yeah. I can't answer that. I should start my video according to the host. Right. Thank you, Aitin. I will. Do you see my video? No, not yet. Maybe. No. Maybe now. No. Now it's on. It's on now? Oh, yes. Okay. All right. I can't see it. But there I am. Okay. All right. Good. No, that's a good question, and I don't know that there's any difference, between the Shias and the Sunnis, in terms of, how anti-science they are. I'm sure there are still some Sunnis who are rationalists, and I'm sure there are still Shias who are rationalists, just as there are Christians of whatever denomination who are rationalists among those Christians who are science denialists. So, I honestly don't think there's a distinction between the various sects they can't. I don't think one outcompetes the other on the subject of science denialism. Okay. The next question is from Stephen Baker. Why was that observatory destroyed? Oh, that's your question, isn't it, Aichi? Yes, I think so. Okay, so I'm gonna cheat and I will just read to you from what I found on the web. But that's also what I kind of remember, like 20 years ago as an undergraduate student, we also taught an Islamic astronomy class back in Turkey. What has happened is that the Sultan wanted to use these observatory and telescopes to have an information about the upcoming Persian campaign. And he asked Taqiyuddin whether he can predict anything about the result of that campaign, and Taqiyuddin said, yeah, sure, go for it. You are gonna have a victory. However, when the army indeed emerged victorious, they were on their way back. An epidemic of the plague spread in the country and decimated the army as well. After that, some other people just wanted to convince the Sultan that actually observatory is not good. Anyone who wants to know the future will be punished by nature, by the God. That's why after it only lasts for 11 years and the Sultan ordered for observatory to be demolished, unfortunately. Yep, so it was used for astrology, as I understand, and instead of for science, and that didn't quite work out the way they thought it would. So. Okay, so the next question is from Alice Gomez. I am familiar with the Spanish term septentrion to find Polaris. It translates roughly as sept equals 7 and En is into, 303 to Uno 1, and refers to the 7 stars of the Big Dipper, then the 3 which point to the 1 Polaris. Septentrional is common on 16th and 17th century Spanish maps to show north. So were the Spanish at least using Polaris as the North Star?
Absolutely right. If we were in the planetarium, I could show you just exactly how precession works and how the various constellations, sort of take the place of each other in being the guidepost to north. And yeah, the septentriones are the 7 stars of the Big Dipper, which we use nowadays to point to Polaris, which is currently the North Star. In various times, historical times, it was the septentriones themselves, or the Little Dipper itself, or Cassiopeia that led navigators to find the way to the north. And now we're lucky to have Polaris, which the name Polaris is actually a modern name from the 19th century that was applied to the star that became the closest star to the north.
Okay. So Alexandra Blunshaft is asking, have you written an article or are you planning a book on this talk, Galen?
Well, thank you for that encouragement. I've certainly done a lot of research on this. I would love to. I think in order to really write, sort of a definitive book on this. I mean, I can write an article, sure, but to write something that has scholarly value, I think I would really need to get my hands on a facsimile copy of one of the Arabic Azyaj, and that's not likely to happen in the near future. I don't have any plans to visit the Bodleian. I have no plans to go anywhere outside the country at the moment. But I don't know, maybe someday, because I'm very interested in the whole thread that goes all the way from Greek astronomy, well, even from Babylonian astronomy through Greek astronomy, through Islamic astronomy to modern day astronomy, and it's certainly something worthy of study. But thanks for the encouragement. I will consider that.
Okay, so now someone has a comment. Without Aquinas, Christian Europe would have gone the same way as Islam.
Sorry, what was that again?
Without Aquinas, Christian Europe would have gone the same way as Islam.
Oh, without Aquinas, Christianity would have gone the same way as Islam. That could well be. I mean, I certainly admire the work of Thomas Aquinas, and certainly putting causality back into physics was an accomplishment of his, and then it was followed up by Francis Bacon and a whole bunch of other people, yeah, I mean that's a very good comment. Of course, Aquinas was very well acquainted with the works of the rationalists among the Islamic and Jewish scholars of the time, in particular Avicenna and Averroes, Ibn Rushd, as I would call him, Ibn Sina and Ibn Rushd. So there was this shared rationalistic school that spanned the cultures of Islam and Christianity in the very late Middle Ages, and certainly Aquinas was a great contributor to the preservation of rationalism within Western culture, or I should say, not the preservation, but the rebirth of rationalism in Western culture.
Another question from Felicia. Do the beautiful tiles from Islam have anything to do with their astrological observations?
Could you repeat that?
Do the beautiful tiles from Islam have anything to do with their astrological observations?
Not, I don't know. I mean, not that I'm aware of. I mean, the Islamic astrologers had their own system, which, like Western astrology, was inherited from the Babylonians and the Greeks. As I mentioned, Al-Battani was the one who criticized astrology and wrote a book in refutation of it. Nevertheless, astrology was certainly prominent in Islamic culture as it is in Western culture today. I mean, I see in the New Mexican on Friday every week in Pasatiempo, an astrological column. We're not going to get rid of those anytime soon. They're here with us to stay. But you know, we need to make a distinction between astrology as a mythology and astronomy as a science. And I still get called an astrologer by people who don't know the difference.
So one comment from my own experience about this astronomy astrology confusion. I got my undergraduate degree in Turkey, and I only realized a few months ago, because when I moved to the Netherlands for my master's and PhD, I needed to have the English version of my diploma. And I did astronomy and physics together for my undergraduate. And the English translation of my undergrad degree is astrology.
No, that's terrible.
That I only realize now, so many years afterwards. I cannot believe it that I didn't pay attention to it before, but that is a fact.
Whoops.
Okay, yep. Okay, next question. Do you know about the Skeptics Society? They have similar concerns about religion versus facts and rational reasoning.
Oh yes, absolutely. I have been, I'm not currently, but I have been a subscriber to their newsletter.
Okay, another question. I have a more optimistic take on your last slide. The Islamic world picked up what the Greeks did, and the modern Western world picked up what the Islamic world did. Even if something happens to stop scientific progress in the Western world, someone else can pick it up.
Good point. Yeah, I mean, I'm not entirely pessimistic about the future in the long term, anyway. You know, I think you know there will be you know scholars in the future, even if during in the short term, the next 100 years or so, even if we are outnumbered and suppressed by anti-rationalists, I think there will be enough skeptics left, rationalists left to pursue science in the future after that.
Okay. Next question. Really, these Islamic astronomers were doing astrology, weren't they? Like Kepler.
Kepler, yes, he was an astrologer for a while, but later in his life he became more critical of it. A number of people have done the same thing, and some people indeed carried on doing astrology even in their later years. Newton, of course, you know, is a great physicist, but he had some very peculiar views, you know, late in life, and you know, things that modern rationalism would not countenance. You know, so you know, people are funny. You know, I mean, there's lots of aspects to a personality, and some people can hold you know, contradictory thoughts in their mind at the same time, and other people try to be, you know, rigorous and rationalistic in all of their endeavors. Kepler was a mix, absolutely, and his you know, the ideas of, you know, conjuring up these regular polyhedra and using them to fill in the spaces between the spheres of the planets and so forth before he eventually settled on elliptical orbits. They all of that thinking had kind of a mystical character about it. You know, he was looking for inspiration from sources that were not purely rational, and a lot of scientists, frankly, do that. It's okay, you know, as long as you end up on the rationalistic side and you know, stick to physics, cause and effect, causality. You know, then you're okay. And you know, Kepler wasn't Newton. You know, he didn't arrive at the physics behind elliptical orbits, but his laws, the laws that he derived from observations of Tycho Brahe and others, enabled Newton to validate his theory.
There's another comment. It appears that science only moves forward by better observations.
Observations are absolutely the key. Yes, and particularly in astronomy, where you can't do experiments, you have to rely on observations, and the more precise your observations are, the better your models are, and in consequence, the better your theory is. You know, that's why I was particularly struck by that cover of Hevelius's book, which had, you know, Alhazen on the one hand and Galileo on the other hand, and explicitly linking the one to theory and the other to observation. Very important. And of course, Al-Haytham wasn't purely a theorist, because he experimented with lenses, and then through his experimentation with lenses derived a theory of optics. But then that theory was used by Galileo and others to make telescopes, to make observations with. You know, so that's an interesting theme in science, the counterplay between theory and observation. And sometimes you need a particular kind of theory to motivate a particular kind of observation. But a lot of times you have an observation that just doesn't fit, and that motivates a new theory. So it's a seesaw.
Yes, so there is a comment on that. Rationality only gets you so far. Where do hypotheses come from? The scientific method does not specify how to generate a hypothesis. Don't they come from intuition?
Where do hypotheses come from? Yeah, absolutely. I mean, it's an idea that comes into your head. Where does that come from to begin with? You know, I always think of who was it? The guy who figured out the structure of benzene, who had a dream about a snake biting its tail, and then realized that the way you could resolve the chemical formula of benzene into a chemical diagram was by making a circle and having the snake bite its tail. You know, dreams are one way of getting inspiration, and I think not. You know, he was not the only one who did that, and I'm sorry I can't remember his name. But other people are inspired by you know, a walk on the beach, or looking up at the stars, or just something. It just comes. I don't know. You know, ideas are precious, and I've had precious few in my life. You know, that are really original and that I could work on. But I've known people who sprout ideas like fountains. I don't know where that comes from. But I agree, it's not something that you can arrive at by deduction. It has to come in from some random firing of the neurons in your brain. And some people ascribe it to religious inspiration. And I'm not gonna say that that's not possible.
Yeah, further comment on that. Einstein had an intuition at the age of 16 that you couldn't travel at the speed of light.
Right. Yeah, and Einstein is famous, of course, for his thought experiments that he could just conjure up in his head.
So the last question is, were the Islamic astronomers threatened for their heliocentric theories and observations? It got stuck.
And elliptical orbits and all that sort of thing, but never published, leads one to suspect that saying my internet connection is unstable. So I don't know. So yeah, we don't know the answer to that. Those, you know, in a tightly controlled society, you know, only things get out that the authorities allow to get out, and in particular, where in a society where you know, before the printing press, for example, where you know, things had to be copied by hand and so forth, and things were very labor intensive. It's probable that people didn't waste a lot of energies on ideas that were certain to be unpopular. But I don't know that any of the people that I've talked about were actually threatened. A good many of them had very long lives and lived, lived to the end of their days and as productive people in their societies. So I don't have any evidence that any of them were threatened. But suppression can take subtle forms in a society. One of the things that one of these articles that I pointed out, I think it was Cheney's points out, no, it was Ofek points out, is that in Islamic culture, there was no separation of church and state. The church and state were the same. One way that he puts it is that Muhammad was both Christ and Constantine. In other words, he was both the prophet and the head of state. And so his followers instituted a government which was run on Islamic principles. And even though people worked in that society who were not Muslim, Christians, Zoroastrians, Jewish, whatever, nevertheless, the fact that there was this central control of both government and religion meant it, in a sense, kind of problematic, perhaps in a soft suppressive kind of way, that you don't go to the trouble of producing a manuscript that you want to circulate to people that is counter to the generally accepted philosophy.
Okay, so Jack and Nell said that August Kekulé von Stradonitz discovered benzene. I hope I didn't butcher the name.
Oh, okay. Oh, that was the discoverer of the
yes.
formula for benzene. Okay, right.
Yes.
Mm-hmm.
Yes. And Alexandra, thanks you for a most interesting and knowledgeable talk. And those are all the questions that came into my chat window. Galen, thank you so much again for sharing us tonight. For everyone, thank you so much for attending tonight's talk. Please visit PEEC website, peeknature.org/events for more talks like this one. Thanks again for tuning in and good night, everyone.
Thank you, everyone, for coming and listening to my talk, and I hope to see you again.